The runaway black hole, a cosmic monster unleashed. In the vast, dark expanse of the cosmos, where galaxies spin through the fabric of space-time like islands in an infinite ocean, something extraordinary has been discovered. Something that challenges our understanding of the universe itself. A cosmic monster has broken free from its chains. Using the most powerful telescope ever launched into space, the James Webb Space Telescope astronomers have confirmed the existence of something that was once thought to be purely theoretical. A runaway supermassive black hole torn from its home galaxy and racing through space at a speed that defies comprehension. This isn't just any black hole. This is a gravitational titan weighing 10 million times the mass of our sun, rocketing through the universe at 2.2 million miles per hour. That's 1,000 kilometers per second, or 3,000 times the speed of sound at sea level here on Earth. It boggles the mind, says Dr. Pieter van Dokkum of Yale University, who led the discovery team. The forces that are needed to dislodge such a massive black hole from its home are enormous. And yet, it was predicted that such escapes should occur. This story begins not with the James Webb Space Telescope, but with its predecessor, the venerable Hubble Space Telescope. In 2023, Dr. van Dokkum and his colleagues at Yale University were analyzing deep space images when they noticed something peculiar. A long, linear streak stretching across the cosmic canvas, unlike anything they had seen before. This wasn't a meteor trail. This wasn't a satellite artifact. This was something far more profound, the wake of something massive moving through space. The black hole is, well, black, and is very difficult to detect when it is moving through empty space, van Dokkum explains. The reason why we spotted the object is because of the impact that the passage of the black hole has on its surroundings. We now know that it drives a shock wave in the gas that is moving through, and it is this shock wave and the wake of the shock wave behind the black hole that we see. The streak measured an astonishing 200,000 light years in length. To put that in perspective, that's nearly twice the diameter of our entire Milky Way galaxy. And at the tip of this cosmic contrail, something was pushing through the fabric of space itself. The streak originated from a galaxy system known colloquially as the Cosmic Owl, a pair of interacting galaxies located approximately 8 billion light years from Earth. The black hole had traveled roughly 230,000 light years from its point of origin, leaving an unprecedented trail of stellar chaos in its wake. But Hubble could only reveal so much. The telescope, while revolutionary in its time, lacked the infrared sensitivity and spectroscopic power needed to confirm what was truly happening at the tip of that streak. That's where the James Webb Space Telescope would change everything. In late 2024, the James Webb Space Telescope turned its golden mirrors toward the Cosmic Owl galaxies. Using its near-infrared spectrograph, or NIRSpec, JWST didn't just capture an image, it dissected the light itself, measuring the velocity of gas being displaced by the object. The data was unambiguous. The measurements revealed a sudden velocity jump of 600 kilometers per second over just 1 kiloparsec, about 3,260 light years. This kind of sharp, localized change could only come from one thing: something massive moving at supersonic speeds through the intergalactic medium. With the JWST, we discovered the huge displacement of the gas at the tip of the wake, where the black hole is pushing against it, van Dokkum says. The shock signatures are crystal clear, and there is just no doubt about what is happening here. The spectroscopic evidence was definitive. The black hole, designated RBH1, Runaway Black Hole 1, was confirmed. This was not just a historic first. It was a window into some of the most violent processes in the universe. The physics of a runaway? To understand the magnitude of this discovery, we must first understand what supermassive black holes are and why finding one so far from home is extraordinary. Supermassive black holes are the titans of the cosmic zoo. They can range from hundreds of thousands to billions of times the mass of our Sunday. Unlike stellar mass black holes, which form from the collapse of massive stars, supermassive black holes occupy the centers of nearly every large galaxy in the universe. our own Milky Way harbors one such monster at its core. Sagittarius A star, weighing in at approximately 4.3 million solar masses. Despite its immense gravitational pull, Sagittarius A star is surprisingly quiet. Scientists have compared its feeding rate to a human consuming just 1 grain of rice every million years. These black holes are gravitational anchors, holding galaxies together with their immense mass. Stars, gas, and dust orbit them in complex dances that span hundreds of thousands of years. The relationship between a galaxy and its central black hole is intimate and fundamental. Each influences the other's growth and evolution over cosmic time. This is why RBH1's escape is so remarkable. To tear a 10 million solar mass black hole from its galactic home requires forces that stretch the limits of physics. As RBH1 barrels through the circumgalactic medium, the diffuse material surrounding galaxies, it creates a phenomenon known as a bow shock. This is similar in principle to the wave that builds up in front of a ship moving through water, but on a scale almost too vast to comprehend. The black hole pushes gas sideways at velocities of hundreds of kilometers per second. This displaced gas glows with characteristic emissions that JWST's instruments can detect and analyze. The velocity of the displaced gas is directly related to the velocity of the black hole, and this is how we determine the black hole's velocity from the JWST data, Van Dokkum explains. It is moving at approximately 1,000 kilometers per second, faster than just about any other object in the universe. It is this high speed that enabled the black hole to escape the gravitational force of its former home. But the story doesn't end with displacement. Behind the black hole, trailing for 200,000 light years, lies something even more remarkable. A stellar nursery. As the black hole plows through space, it compresses gas in its wake. This compression triggers gravitational collapse, and from that collapse, new stars are born. The runaway black hole isn't just destroying, it's creating. In its violent passage through space, it's seeding the universe with new generations of stars. This discovery reveals a profound truth about the cosmos. Even in destruction, even in chaos, the universe finds ways to create. How does a black hole go rogue? The question that naturally arises is, how? How does a supermassive black hole weighing millions of times the mass of the sun achieve escape velocity from its own galaxy? The answer lies in one of the universe's most spectacular events: galaxy mergers. Galaxies are not static. They move through space, pulled by gravity into complex cosmic dances. When two galaxies approach each other, their gravitational fields begin to interact. Over millions of years, they spiral closer and closer, eventually colliding and merging into a single, larger galaxy. Mergers happen often in the life of a galaxy, Van Dokkum notes. Each galaxy with the size and mass of the Milky Way has experienced several during its lifetime. So, black hole binaries should form pretty regularly. Each of these colliding galaxies brings its own supermassive black hole to the cosmic smash. When the galaxies merge, their central black holes sink toward the center of the newly formed galaxy, where they encounter each other in what can only be described as a gravitational showdown. It's at this critical moment when supermassive black holes meet that the conditions arise for a runaway event. The first mechanism that could eject a supermassive black hole involves the merger of two black holes and the asymmetric emission of gravitational waves. When two black holes orbit each other, they emit gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity and first directly detected in 2015 by LIGO. As the black holes spiral closer, they emit these waves in all directions. But here's the crucial detail. If the black holes have different masses or are spinning at different rates, the gravitational waves they emit can be stronger in one direction than another. This asymmetry creates what physicists call a recoil kick. When the black holes finally merge, the newly formed black hole can receive an enormous push from the momentum carried away by the gravitational waves. The gravitational radiation released in that merger imparts a powerful kick to the newly formed black hole. Van Dokkum says, that kick could impart a speed of 1,000 kilometers per second, enough to eject the black hole. For RBH1, this would mean that the black hole we observe today is actually the product of an ancient merger, two black holes that became one, and in doing so, received enough momentum to escape their galaxy entirely. The second mechanism is perhaps even more dramatic: the three-body interaction. This scenario begins with a binary system, two supermassive black holes already orbiting each other at the center of a galaxy. This could occur when one galaxy has experienced a previous merger and never quite settled into a single central black hole. When a third galaxy merges with this system, it brings its own supermassive black hole into the mix. Now we have three massive objects in close proximity, each exerting tremendous gravitational forces on the others. When a third black hole enters the binary system, it becomes unstable, and one of the three black holes will get kicked out of the system, Van Dokkum explains. Three-body systems are notoriously unstable. Unlike two-body systems, which can maintain stable orbits indefinitely, three-body systems are chaotic. Small perturbations can lead to dramatic changes in the orbits, and the mathematics describing these interactions is among the most complex in physics. In this cosmic game of gravitational pinball, one black hole inevitably loses. The interactions can fling it outward at tremendous velocity, easily enough to exceed the escape velocity of even the most massive galaxy. So which mechanism created RBH1? The truth is, we don't yet know for certain. However, researchers have some educated guesses based on the object's properties. What we don't know is how quickly these binaries merge, if at all, and how often the resulting kick removes a black hole, Van Dokkum says. My view is empirical. Now that we know how to look for them, we can find other examples, and then we can answer the question directly from data by counting the number of escapes. The scientific community leans slightly toward the merger kick scenario for RBH1. The black hole's velocity and trajectory are consistent with what models predict for gravitational wave recoil. However, without direct observation of the merger event itself, which occurred billions of years ago, definitive proof remains elusive. What's clear is that both mechanisms are physically plausible, and both likely occur throughout the universe. RBH1 may be the first confirmed runaway supermassive black hole, but it's almost certainly not alone. JWST's black hole revolution. The discovery of RBH1 is just one piece of a much larger revolution in our understanding of black holes, a revolution made possible by the unprecedented capabilities of the James Webb Space Telescope. Since beginning science operations in July 2022, JWST has fundamentally transformed our view of the early universe and the black holes that inhabited it. One of JWST's most perplexing discoveries has been a class of objects nicknamed little red dots, or LRDs. These are compact, extremely red sources that appear in large numbers around 600 million years after the Big Bang, only to largely disappear about 1.5 billion years later. Little red dots have mystified astronomers because they don't conform to our understanding of how galaxies and black holes co-evolve. These luminous objects are either far too dense to account for their stellar masses, or they harbor supermassive black holes that are far too massive for such small galaxies. In November 2024, JWST confirmed an actively growing supermassive black hole within the galaxy. This means that Canucks LRD Z86, existing just 570 million years after the Big Bang. This black hole was feeding voraciously and growing rapidly, far faster than theoretical models predicted was possible in such a young universe. The discovery challenged fundamental assumptions about black hole formation and growth. Another remarkable discovery involved a galaxy designated Virgil, observed as it appeared just 800 million years after the Big Bang. When viewed in visible and ultraviolet light, Virgil appears unremarkable, just another star-forming galaxy in the infant universe. But when JWST's mid-infrared instrument, or MIRI, turned its sensors toward Virgil, the galaxy transformed. Hidden beneath clouds of dust was a supermassive black hole accreting material at a rate far exceeding what should be possible for a galaxy of its size. Dr. Marcia Ricci of the University of Arizona summarizes the paradigm shift. JWST has shown that our ideas about how supermassive black holes formed we're pretty much completely wrong. It looks like the black holes actually get ahead of the galaxies in a lot of cases. That's the most exciting thing about what we're finding. Before JWST, astronomers believed galaxies formed first and gradually nurtured black holes in their cores, with both growing in lockstep over billions of years. This view was based on observations of the local universe and extrapolations backward in time. JWST has shattered this paradigm. The telescope has revealed supermassive black holes existing when the universe was barely 300 million years old, a cosmic eye blink after the Big Bang. These black holes are not small. They're already weighing in at millions or even tens of millions of solar masses. The problem is this. According to standard models of black hole growth, there simply hasn't been enough time for these monsters to form through conventional means. In July 2025, JWST made another groundbreaking discovery that might help solve this puzzle. Astronomers observed a peculiar object dubbed the Infinity Galaxy due to its distinctive double ring shape. At the center of this galaxy, between two nuclei, sits a supermassive black hole that appears to have formed through a process called direct collapse. Unlike the traditional pathway, where a star collapses into a stellar mass black hole that then grows through accretion and mergers. Direct collapse black holes form when an enormous gas cloud collapses directly into a supermassive black hole without ever forming stars. We think we're witnessing the birth of a supermassive black hole, something that has never been seen before, Van Dokkum says of this discovery. Direct collapse requires very specific conditions. The gas cloud must be massive, it must be extremely hot to prevent fragmentation into stars, and it must collapse rapidly enough to overcome internal pressure. In the early universe, when galaxies were colliding more frequently and gas densities were higher, these conditions might have been more common. If so, direct collapse could explain how supermassive black holes reached such enormous masses so quickly. JWST has also revolutionized our ability to observe one of the universe's most violent phenomena, tidal disruption events, or TDEs. When a star ventures too close to a supermassive black hole, the black hole's gravity creates tidal forces that literally tear the star apart. Half the stellar material falls into the black hole, while the other half is flung into space. The result is an enormous burst of energy, a cosmic beacon announcing the black hole's presence. In late 2025, astronomers at MIT and Columbia University used JWST to peer through the dust of nearby galaxies and observe several TDEs with unprecedented detail. What they found was surprising. Many of these events were occurring around dormant black holes that experience little activity until a star happens to pass too close. Megan Masterson of the MIT Kavli Institute explains. These are the first JWST observations of tidal disruption events, and they look nothing like what we've ever seen before. The fact that we're now able to study what that dormant black hole environment actually looks like is an exciting aspect. The implications? The discoveries enabled by JWST are forcing astronomers to completely rethink the standard model of galaxy evolution. The old paradigm was straightforward. Dark matter halos form first, collapsing under gravity. These halos attract normal matter gas and dust, which cools and condenses to form stars. Eventually, some stars collapse into stellar mass black holes, which merge over time to form supermassive black holes at galactic centers. This process should take billions of years. Yet JWST is finding fully formed supermassive black holes existing when the universe was mere hundreds of millions of years old. Several new theories are emerging to explain these observations. First, star formation in the early universe may have been far more efficient than previously thought. Higher gas pressures, elevated temperatures, and the presence of magnetic fields could have allowed galaxies to convert gas into stars at astonishing rates. Second, direct collapse black holes may have been common in the early universe, providing heavy seeds that could grow into supermassive black holes much faster than stellar mass black hole seeds. Third, the relationship between black holes and galaxies may not be as coevolutionary as believed. Black holes might actually get ahead of their host galaxies in many cases, growing faster and earlier than the galaxies themselves. The confirmation of RBH1 has opened a new field of observational astronomy. the systematic search for runaway supermassive black holes. The obvious data sets to look for these features in a systematic way are wide field surveys with Euclid and Roman, Van Dokkum notes, the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will scan wide swaths of sky with clarity approaching that of Hubble. Combined with machine learning algorithms trained to spot the characteristic long, needle-like streaks left by runaway black holes, these missions could discover dozens or even hundreds of similar objects. Each new discovery will provide more data about the mechanisms that eject these cosmic giants. By counting the number of runaways and studying their properties, astronomers can test theories about black hole mergers, gravitational wave recoil, and three-body dynamics. These discoveries aren't just about distant galaxies and ancient history. They're about understanding the universe we inhabit today. Our Milky Way has experienced several major mergers during its 13.6 billion year lifetime. Each merger likely brought new supermassive black holes into our galactic neighborhood. What happened to those black holes? Did they merge peacefully with Sagittarius A star, the supermassive black hole at our galaxy's center? Or were some ejected, sent on lonely journeys through intergalactic space? The answer could lie in the halo of our galaxy, where astronomers have found puzzling stellar streams and unusual gravitational signatures. Some of these might be the remnants of ancient close encounters with runaway black holes. Underlying all of these discoveries is the mysterious presence of dark matter, the invisible substance that makes up approximately 85% of all matter in the universe. Dark matter doesn't interact with light, making it invisible to telescopes. We know it exists only through its gravitational effects. Dark matter forms the scaffolding upon which galaxies are built, creating gravitational wells that trap normal matter and allow stars and black holes to form. JWST's observations of early galaxies are providing unprecedented insights into how dark matter halos formed and evolved. The rapid appearance of massive galaxies in the early universe suggests that dark matter structures formed faster than previously thought, or that they were more efficient at drawing in normal matter to seed star formation. These findings connect directly to fundamental questions in physics. What is dark matter? How does it interact with normal matter? And what role does it play in shaping the large-scale structure of the universe? The future of black hole astronomy? The James Webb Space Telescope is just the beginning. A new generation of observatories is being planned that will push our understanding of black holes in the early universe even further. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter, 4 times larger than any existing optical telescope. Its sensitivity will allow it to study individual stars in distant galaxies and probe the environments around supermassive black holes with unprecedented detail. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will be a space-based gravitational wave detector. Unlike ground-based detectors like LIGO, which detect high-frequency gravitational waves from stellar mass black hole mergers, LISA will detect low-frequency waves from supermassive black hole mergers, exactly the events that might create runaway black holes. LISA will allow us to detect these mergers as they happen, millions or billions of light years away, and measure the kick velocity imparted to the merged black hole. This will provide direct observational evidence for the gravitational wave recoil mechanism. The future of astronomy lies in combining multiple types of observations, what scientists call multi-messenger astronomy. By observing the same event with electromagnetic telescopes like JWST, gravitational wave detectors like LISA, and potentially even neutrino detectors, astronomers can build a complete picture of the most violent events in the universe. The journey continues. The discoveries continue, and our understanding deepens with each observation, each new piece of data, each stunning image that reveals the cosmos in all its glory. This is the promise of the James Webb Space Telescope, and it's a promise being fulfilled every day. Thank you for watching this scientific overview. Subscribe for more updates on space missions, and share your thoughts in the comments. Which aspect of these missions interests you most? Till next time, keep exploring the cosmos.